Okay, so today we're going to talk about the competition between substitution and elimination reactions. We've covered these individually before, and we studied in detail the 4 different mechanisms, SN1, SN2, E1, and E2. In a real situation, you've got competition between these different mechanisms, and we often want to pick one that's going to win, but there doesn't have to be one winner. There can be multiple products, and we need to be able to predict what major and minor products will be formed. And the steps in doing that are here, determining the function of the reagent, determining the expected mechanism, and then considering regiochemical, stereochemical requirements specific to those mechanisms. So we'll probably get through 1 and 2 today. Determining the function of the reagent. Well, we've talked about nucleophiles and bases. Nucleophiles are going to attack the alpha carbon. And here I just drew a little substrate here. Z is our reagent. When the reagent acts as a nucleophile, it goes along this way, and it's going to attack the alpha carbon. That's going to result in a substitution reaction. So if your reagent is acting as a nucleophile, you can get substitution. When your reagent is acting as a base, it's going to attack the hydrogen that's on the beta carbon, and that's this arrow over here. So if it's acting as a base, it's going to attack the hydrogen. You're going to get an elimination reaction. What's important to understand is that nucleophilicity and basicity are not the same concept, and they don't necessarily correlate. You can have a strong nucleophile that is a weak base. There's different combinations possible. So we have to look at those. What makes a strong nucleophile? Strong nucleophiles tend to have negative charges. They need to be polarizable, and they need to be sleek. What do I mean by sleek? Not bulky. The nucleophile will attack the carbon. It needs to be able to get in there. So you can think of it like a missile, a nuclear missile, nucleophile, nuclear missile. It needs to be able to get in. If it's big and fat and bulky, it's not going to fit in among these other groups. Strong bases, we can think of the strength of the base in terms of acid-base chemistry. If the base has a conjugate acid that is strong, the base will be weak. If the conjugate acid is weak, the base is strong. So that's one way to look at it. The other is REO, which we've talked about before. What element, what atom it is, resonance effects, induction, and orbital effects, and that can help us to predict if it's a strong base or not. For bases, bulk is not a problem. And so here's just a very sketchy overview of the 2 different types of mechanisms. The unimolecular, this is the unimolecular, where a carbocation forms first, and then the reagent attacks, and the bimolecular, where it's a concerted mechanism. The nucleophile or base is attacking while the living group leaves. And so we've got different combinations. And I remember as a student really struggling in organic chemistry with all these crazy things that I was expected to remember. And I'm not good at just memorizing stuff randomly. And I think most students aren't either. And so I want to help you organize this stuff so that you can remember it for an exam. Because it's one thing to have the book and do the problems and be able to look at the nice little charts, but you don't have that on an exam. So I made this little grid here. And I'm going to put the base at the base of the grid. And we're going to say as we go over this way, the strength of the base increases. And we're going to look at nucleophile strength going up this way. So there's going to be 4 different combinations. We have strong or weak nucleophile and strong or weak base. So down here, this would be weak base, weak nucleophile, strong nucleophile. So we end up here, weak nucleophile, weak base. And that's not 2 reagents, that's 1 reagent that is a weak nucleophile and a weak base. Up in this box, we get a strong nucleophile that is a weak base. Up in this corner, we're going to have a strong nucleophile that is also a strong base. And down here, we've got a weak nucleophile that is a strong base. So there's 4 different possibilities when we're looking at our reagent. Then to predict the mechanism, we need to think about what sort of mechanism does each of these types of reagents favor. Well, a strong nucleophile, strong base. When the reagent is strong, the bimolecular reaction mechanisms are favored. And so we're going to see E2 and SN2 will most likely be competing in this situation. This reaction is faster in general than the unimolecular because here we're waiting for the carbocation to form. That's the limiting step in the mechanism, and that is slow. So if we have a strong nucleophile, strong base, we're going to get the bimolecular mechanisms predominating. Down here, weak nucleophile, weak base, the rate of the bimolecular mechanisms depends on the strength of the reagent, in part. And this gets beat out because it's slow. If this mechanism is slowed down because we have a weak nucleophile, weak base, then we have a chance for the carbocation to form, and we can have that unimolecular mechanism happening. So down here, we're going to see E1, SN1 competing. Up in this corner, strong nucleophile, strong base. So it's really not, strong nucleophile, weak base. It's really not functioning as a base at all. It's a strong nucleophile. What do nucleophiles do? Do we get elimination or substitution? Substitution. So strong nucleophile, we're going to get substitution reactions. So we're going to get SN1 and SN2 competing here. It's a weak base, we're not going to get elimination. Down in this corner, it's a weak nucleophile. We're not going to get the substitution, we're going to get the elimination reactions. So we're going to be looking at E1 and E2 happening. Any questions? If you can think this through, you get to the exam, you could write this chart out from your memory before you look at the questions and lose your mind, right? And then you can refer back to it. That's not cheating. Okay. Well, let's look at some specific reagents and how we could classify those. This is a table from your textbook. This group, your book classifies as nucleophile only. In my categorization, we're calling that strong nucleophile, weak base. They don't function as bases. They only function as nucleophiles. Here we've got that. Hate it when I do that. Here we have the halides. Those are the conjugate acid of these are strong acids. So these are weak bases. That's why they don't function as bases. They're good nucleophiles, though. And here we have sulfur nucleophiles. I don't know what's doing that. Fine. I don't know what's up with that. What is it doing? Great. This never happens. Okay, computer glitch. This ongoing disagreement with my computer. Strong nucleophile, weak base. We covered that one. Next group, book says base only. So that's a weak nucleophile, strong base. So base only, we've got the hydride ion. This is a strong base, but it doesn't function as a nucleophile very well because it's so small. It's a hydrogen with one extra electron. Tiny little guy. Too small to be polarizable, so it can't function as a nucleus. It's really small, so it could get in there just fine. And then we've got DBN and DBU, which you've probably never seen before. Here are their structures in their names, and you can see why we call them DBN and DBU instead of by their full names. These are good bases. They don't function well as nucleophiles because they're bulky. We've got these double rings going on here. They're not going to be able to get in, and so they're only functioning as bases. Then we've got the strong nucleophile, strong bases, and the weak nucleophile, weak bases. And again, it can be hard to remember which ones are in which category. So I often turn to less scientific things to help me remember stuff. And students seem to appreciate that as well. So looking at these guys, water, methanol, ethanol, those are solvents. They're, stable, not very reactive. They're not known to be particularly acidic, right? So if anything, they're going to be a weak acid or a weak base. They're not strong anything. So these are weak bases. They're weak nucleophiles. They don't have a charge. They're just not particularly aggressive in any way. If we take the hydrogen off of these guys, we get these, the conjugate bases. If these are weak acids, then these are going to be strong bases. And I look at these and I think, do those guys look happy? They're going to be just real happy with themselves, or are they going to go after hydrogens? Well, these guys look like they want to go after hydrogens, and they do. They act as strong nucleophiles. They're sleek. They can get in there just fine, and they have negative charges. They're strong bases because their conjugate acids are weak. And then there's this guy, T-butoxide, and your book puts him over there, and technically he could be a nucleophile, but he's kind of bulky. And so I would take this guy and stick him in this category over here. Generally functions only as a base. So you kind of have to watch out for him. So then let's look at the effect of substrate. That's what we have to consider when we determine the actual mechanisms that we're going to see. So if we've got a reagent that's functioning only as a nucleophile, nucleophiles give us substitution reactions. So then we're identifying, are we going to have SN1 or SN2 going on? And here we need to look, is the substrate primary, secondary, or tertiary? And I skipped the slide. Okay, let's go back and fix that. Oh, SN1 and SN2. There we go. We need to look at primary, secondary, or tertiary. Well, if we think about the mechanism, a primary substrate, in order to undergo an SN1 reaction, is going to have to form a carbocation. It's not stable, and so we're only going to get the SN2. The tertiary substrate will form the carbocation just fine, so we can have the SN1 reaction, but because of steric hindrance, we're not going to get the SN2 happening. And so for tertiary, we'll only see the SN1. For the secondary, we'll get a competition between the two. When we look at things acting as a strong base, bases give us elimination reactions. We're going to have E1 and E2. Here what we end up with, though, is E2 predominating for all of them, because this is a strong base. And so the bimolecular process happens quickly, and there's really not much time for the unimolecular process to occur at all. And then we have strong nucleophile, strong base. So this one, the tertiary, is easier to think about. Strong nucleophile, strong base, we're comparing the bimolecular processes, the dang it, I did it again. The SN2 and E2. Tertiary can't undergo SN2 mechanism because of steric hindrance, so we're only going to get E2. For primary and secondary, it's helpful to remember this relationship. These SN2 mechanism is very strongly dependent on the order of the substrate. There's really no SN2 occurring for a tertiary, and it's very fast for the primary, and that has to do with steric hindrance. The E2 reaction is somewhat dependent. It actually gets a little faster as the order increases, but not as much. So for a primary, we've got the SN2 being occurring faster, so that will give us the major product, and E2 will give us a minor product. For the secondary, it's reversed somewhat, and so we'll get more of the E2 product and less of the SN2 product. And then for the last one, weak and weak. So this ends up not being terribly useful. The primary we're looking at SN1 and E1, but they are so slow for the primary that it's just really not practical. Okay.